All right. So,
Before we jump into things today, I think I'm going to do a little bit of Excel first, and then we're going to jump into the last, two more types of examples that you might see in that Connect homework. But as I move to due date, I think kind of finishing that up Wednesday should still give you plenty of time to answer all the questions. Should be able to chip away at a few more today after we kind of go back, after we're done with Excel and whatever we cover for the rest of the remaining time.
but to start out on Canvas, files, where is it at? In-class data. We're going to be using this to-population HT blank file, right? So I've got it pulled up here. I've got a lot of different worksheets. We'll kind of keep working on this, and as I work through, I'll kind of post what we do in class as like an in-class work file up there. So the blank when we start out, and we've got these South and Midwest schools, right? So we'll do some confidence intervals, and we'll do some hypothesis testing. So just as a kind of reminder, we want a confidence interval for the difference between two groups. And here, we're going to end up with having some universities that are in the South and universities considered to be in the Midwest. We're then going to go a certain number of standard deviations away. That gives us alpha over 2 on each side of our confidence interval. We then multiply that by the number of standard, whatever that standard deviation is, which is just each group's variance over that group's sample size. Okay? We then had kind of a very similar thing when we were looking for the difference in sample means, but we wanted to turn it into a test statistic. Well, we took the sample statistic we found. I can kind of think about this as the hat even. The assumed true value of that difference, we said we'll always use 0, and then we're dividing by the standard deviation of that statistic, which just said what that was for our confidence interval. It's going to be the exact same. Okay. So what do we need to first do, right? So in a lot of these problems we work through in class, we're given these sample means, we're given these sample sizes. We're actually doing this in practice. We need to calculate these from some data sets. Now, we're going to walk before we can run. We'll eventually look at some examples today where if we only have the sample variance, what do we do? But for right now, we've got some known population variance that was given to us. Okay. We're then going to find the sample mean. So I'm in that Midwest sheet first. I'm going to go over here, and I'm just going to look at total undergraduates, right? So I'm going to see are schools in the Midwest any different when it comes to size than for schools in the South, right? Hit enter, got my sample mean. How do I find my sample size? Well, that's just the count function. This should be kind of review stuff here. Select that variable. I've now got my sample mean, my sample size, and the population variance for my first group. Well, my second group is going to be schools in the South, right? So it's a different sheet. You have a question?
Which column was that we went to the sample mean?
So we're just looking at the total undergraduates here. Right? So, we could do this for different, whatever variable we're interested in. We could do male, female. I think that might be the only other ones we have here. But yeah, we're going to be using that column H. Right? So we've got the sample mean, the sample size, and this known population variance for group 1. We need the exact same thing for group 2. Right? So for the South, I need to find the average or the sample mean, and I go over, well, here's the total undergraduate variable in this data set. Control Shift, Command Shift on a Mac, hit the down arrow, hit enter. Right? If I want my sample size, use that count function, go over to that total undergraduate variable, Control Shift, Command Shift on a Mac, hit the down arrow, hit enter. I've now got my second groups, sample mean, sample size, and once again, I had to be given this known population variance. Okay. Now, one thing that I don't think I've showed you yet, you can do in Excel, is you can actually reference across sheets, right? So every cell reference we've ever used, it's been in the same sheet, right? So cell C10 or B12, right? But what I'm going to do is here, I've already calculated this, but it's in a different data set, right? It's on a different worksheet. So I'm going to put an equal sign, right? I'm then going to click on the worksheet where I know the Midwest data is at. And then I'm going to go over here. Well, where was the sample mean for the Midwest? It's in this cell. So notice, and I can't zoom in on this formula bar, but basically I'm referencing cell M4 from that Midwest data sheet. Okay? But an easier way, so that it just automatically puts that, you don't have to type it in there. Just start your equal sign, go to the Midwest worksheet, and then select the cell that you want to put over there. Now I'm going to hit enter. It's going to send me back, and now it just transfers that sample mean over to this other worksheet. So I'll show you exactly how I do this with the sample size as well. So if I go equal sign, that's going to say, okay, anything I click on now, if I click on a cell, if I click on a worksheet, Excel's automatically starting to throw references in there. So I click on that Midwest worksheet, notice it throws that reference. I then click on the sample size on that worksheet for the Midwest schools, it throws that in there. Now, if I start clicking on other cells to like try to get out, I'm going to have some issues. So once I've got the cell selected, I just hit enter, and it's going to send me right back out to the cell, kind of, get me out of that cell so I don't, it's not putting any other references I click on anything. Okay. Any questions on that idea before? No questions on that? Okay. So I've now got the 6 things that I need. 2 sample means, 2 sample sizes, 2 known population variances. The only thing left I need to do to build a confidence interval is figure out that z-value. Well, this looks exactly like we did what you should have been doing on that last Excel, right? For our confidence intervals for one population. All we're going to do is say, look, we want this z-value that's going to give us a total of alpha on either, alpha total outside of our interval, which means if I've got 2 sides, I've got half of alpha on each side. Okay. So how can I do that in Excel? Well, we had that norm.s.inv where we're looking at a standard normal distribution. We're looking at z-values. I know the area I want in the tail, and I want Excel to kind of spit out the z-value. So norm.s.inv, we knew the area in the tail, it's going to give us a z-value. Norm.s.dist, we knew the z-value, it's going to spit out us the area in the tail. So we're working kind of in the inverse here. We know the area in the tail we want, and that area is going to be alpha divided by 2. Now, what's one problem going to be if I just hit enter here?
It's not going to give you the absolute value.
Yeah, right. So anytime I'm using that norm.s.inv, it's just like the physical table. It's the area in the left. So if I'm looking up the area in the left, I'm always going to find the negative value. But that's kind of already baked into my lower and upper bound equation. So I really just need the absolute value of that. So I'm just going to go over here, use that absolute value function. Okay. Because you technically don't have to, like multiply it by -1 if you wanted to. There's other tricks, but right, we just want to drop that negative sign. I'm then going to just copy this down. It's going to update those alphas. I've now got those 3 z-values relatively quickly. So you start out with that norm.s.inv. You just tell it the area you want in the tail, which we know is alpha over 2. It's going to give you that number of standard deviations away you need to go, right? And then we said, well, we've kind of already got this positive and negative built into our formula for the lower upper bound. So we're just going to hit enter. So I hit enter. The next thing I'll do is, well, all I'm using Excel to be now is my calculator. This is just a formula. I have every single value somewhere in this worksheet. It's just using Excel to be a calculator. Instead of typing in the numbers, I'm just clicking on the cell where the numbers are. So what's another way I can make this a little bit easier? I'm going to do this in a separate cell. So they just have one value. So that it just looks a little bit cleaner, right? So the standard deviation of the difference in my sample means, well, that's just the square root of what? Each group's population variance divided by that group's sample size. And I've got this, this is what? M6 plus that group's sample size. Oops. That group's population variance divided by that group's sample size. Right? So all I'm doing is using Excel to be my calculator to give me that standard deviation for the difference in my sample means. Okay. Once I have that, so I can hit enter, it'll close that parentheses automatically for me. Well, then it's just a matter of, I've got 1, 2, 3, 4 things. I'm using Excel to be my calculator to find that lower and upper bound. So I go down here. What do I base my confidence interval around? I'm going to take the South. Actually, did I say how the difference between Midwest and South? Okay, so Midwest minus the South. Right? I'm then going to subtract however many standard deviations away I need to go for this, what, 90% confidence interval, right? That alpha of 0.1. So I click on that Z value. I then multiply that by, well, what is the standard deviation of this statistic I'm looking at? I'm looking at the difference in means. I calculated that standard deviation up here. Okay. That's all I'm going to do from I'm just using Excel to be my calculator. I've already got the numbers calculated up here. Just got to click on the cells those numbers are in. Okay. Any questions on anything at this point? Want to see a cell again? Yeah.
The sample,
This guy?
yeah, that one.
Yeah, so we're just taking each group's population variance, dividing that by that group's sample size, adding them together, and then taking the square root of that entire thing. Other questions to this point before we keep moving?
Actually,
Yeah.
The lower bound.
Yep. So if I copy this lower bound down, when I build different levels of confidence, the only thing that's changing is what? My sample means changed? No. My sample size has changed? No, I'm looking at the same data. Do my known population variances change? No, I'm looking at the same. The only thing that changes is my alpha, which then changes what Z value or the number of standard deviations away I need to go, right? So when I copy this down, I really want everything to stay the same except for that Z value, right? For each one of these different levels of confidence, I want that lower bound to update. So I'm going to go through, select these guys, hit F4 or FNF4 or Command T on a Mac. And also on some Macs, if you have a function key or an FN key, it'll be FNF4 for you as well. I think some of the newer Macs have those. If not, it's Command T. And then I select that because I don't want that to change. Now, when I copy this down, the only reference changing is that Z value, right? Which is what I wanted to update, right? For every different level of confidence. So I can hit enter, copy this down, and I've got my 3 lower bounds relatively quickly. If I'm wanting to get my upper bound, what do I need to do? What's the equation going to be for that? Everything's exactly the same. So we said one way that's kind of easier to do that is if I drag it over. I noticed a couple people made this error on the last Excel. If I copy this over, thinking, oh yeah, I'll have the same thing. We'll notice, oh, it updates that Z value reference to the lower bound. Well, that's not what I wanted to use. So probably an easier way to do that is just go in, copy that formula, hit enter it out of the cell, paste it. Now it's the exact same formula. All I have to do is go in and change that negative to a positive sign, right? The only difference when I'm calculating my upper bounds, I just add that margin of error. Okay. Any questions up to this point? You want to see a cell again? Okay. So I copy this down. I've now got my upper and lower bound pretty quickly. You'll kind of notice at higher levels of confidence, that means I'm going to have a smaller alpha. So the area in my tail is getting smaller. So the Z value should be getting larger, which means I'll have a wider interval. So notice as I go to higher levels of confidence here, 90 to 99, my lower bound gets lower and my upper bound is getting higher, right? I'm getting a wider interval. Okay. Before we move to the next thing, where do I have this set up? Way down here, of course. Well, we'll go down here. So let's say, make sure, yeah, this is going to make sense. So let's say we want to do a right tail test, right? Where I want to know, is the difference between Midwest and Southern schools enrollments, is that difference positive? Do Midwest schools have larger on average enrollments? Right now, I bet this is 2000. We're going to go in and change this to 0. I shouldn't have done this here. I'm going to show you something before we're done, but for now, let's keep this at, oh, come on. 0. And you don't have to worry about changing this text box if you don't want to. We just need to make sure that we have that hypothesized value of 0 in the cell so we can reference it. And actually, we don't even need to reference it necessarily. I'll kind of show you why it can be useful to do that though. So we've got this assumed true difference of 0, and we've got a right-tailed test. Okay? So we're going to first find our test statistic. This point is just having Excel be our calculator. I wish there was a nice built-in function for this. We're just going to have Excel be our calculator. Okay. So what are we going to do? We're going to take our sample difference. So go up here. And I wish well, go up here. Take the Midwest sample mean, subtract the South sample mean. Right? So, whoops, I've got that there. Now the next thing is, I've got an assumed true difference of 0. Do I really need to subtract that? No. I'm going to only so I can show you it is possible to use values other than 0, even though I'm not going to expect you to do that in this class, right? And I'll talk a little bit about what that looks like, how that's different once we get there. So I could subtract this cell that has the 0 in it, but really if I'm using the assumed true difference of 0, I don't really need to do that, right? I'm just setting this up so I can change that assumed true difference later on. Okay. So I've got my numerator. Well, this is where if I've kind of done some of these intermediate calculations, I've already calculated this, right? I already found that standard deviation of the difference in my sample means when I was building confidence intervals. So instead of typing all this in again, all I have to do here is simply divide by, go back up here. Oh, I had the standard deviation for my sample means in this cell, right? So if we're building confidence intervals and doing these hypothesis tests simultaneously, we can kind of reuse some of our work. Now, if we didn't, what I would probably do is still calculate this in a separate cell so they just have one value to reference, right? But that's that's all we're doing in Excel for our test statistic is using it as a calculator. Okay? So I hit enter here. I get a test statistic of about 2.6. Right? So got my test statistic. It's what, 2.6? If I wanted the p-value for a right-tailed test, that's the probability I saw something as inconsistent with what I assume to be true, or even more inconsistent, but with positive values, it's like a greater value. For a left-tailed test, that would be anything less, right, to the left. So for a right-tailed test, we want the area to the right. So what can we do? Well, I said earlier, if we know, right, remember this test statistic, we sometimes call a Z statistic because it's a test statistic coming from this standard normal distribution. It still represents a Z value. So if I know the Z value, I want to find the area in the tail. We said what equation I said earlier could we use? Norm dot S dot dist. Yep. So we're using that standard normal distribution. Our Z value is right here, right? Comma, we're always going to make it cumulative. And that always is going to give us that cumulative probability, that area to the left. Now, the problem is I wanted the area to the right, right? So even if I forgot that and I hit enter here, one way to check myself, what value is my standard normal distribution centered around? The whole reason it was a standard normal distribution is it had a mean of 0. Right? So I automatically know my p-value has to be less than what? Yeah, half or 0.5, right? The area to the left and the right of the mean is 0.5. I'm looking at something smaller than that. So if I hit enter, I look at this and go, ooh, I did something wrong, right? Well, what did I still need to do? If this norm.s.dist gives me the area to the left, how can I find the area to the right? Yeah. So we just go, you can do it all in one cell, 1 minus that. Okay. Now, if I hit enter, now I get a p-value that's relatively small, which kind of makes sense. 2.6 standard deviations, once again, might not be super familiar, but that's anything over 2 standard deviations, we're starting to get kind of far away. So now that I've got this p-value, I could do kind of my rejection decision. So I'll show you 2 ways we can do this. So first, I showed you this with one population, is just use that if statement, right? And we say, okay, look, if my p-value is less than alpha, that's a situation in which we'll reject. Okay. Well, I've got my different alphas set up here, right? So if this p-value is less than alpha, comma, if that's true, I should be putting the word, I think I put my caps lock on. There we go. I should put the word reject in there, right? I'm rejecting the null at that level. Comma, if it's not true, I'll just put the word fail in there, but you can type out fail to reject if you really wanted to, right? But just to kind of keep it small, right? So I use that if statement. What do I want to check to see if it's true? Is that p-value less than alpha? Well, I've got those in two cells, so I can just type it out. If that's true, I should be rejecting, so put the word reject. If that's not true, put the word fail to reject or fail. Now, if I copy this down to make rejection decisions at each one of these alphas, what's going to be a problem? The alpha is going to change, which that's what I want, right? So when I copy that down, I want to keep updating my alpha, right? Because at different levels of confidence, I'm comparing to a different alpha. What doesn't change? So I should probably go in and freeze that cell reference. Now, when I copy this down, I'll get my rejection decision at all three levels. Now, this one, they're all reject because even at an alpha of 0.1, I've got this really small p-value, right? Any questions on anything there? You want to see something again, or just that question, John? Okay. So we have one other approach we could have used, which was the critical value approach, right? So this is where we figured out what critical values gives us certain amounts of alpha in the tail, then plot our test statistic against it, right? So how can I find critical values? So just as kind of a reminder, it's very similar to what we did with confidence intervals. What we're trying to do, for instance, oh, sorry, I'm not doing a two-tail test, we're doing a right-tail test. So I want the critical value that gives me an alpha of 0.1 in the tail here. So I don't know what this z value is. I don't know what this cutoff z value, this critical value is, but I know the area in the tail I want is 0.1. Well, here's where it gets a little tricky, because when we use these functions in Excel, or when we use the table, we always are looking up the area to the left, right? So technically there's two ways I could do this. The first is I could just say, okay, look up that area I want in the tail. So use that norm.s.inv, right? Say, I want alpha total in my tail here. Tell me the number of standard deviations that gives me 0.1 in the tail. The problem is that's going to be looking at the left tail. So it's going to give me the correct value, except for it's going to be negative. So what I could do is just say, oh, I know this is a right-tailed test. Whatever z value has 0.1 to the left is going to be negative, and have the same area, that 0.1 to the right of that value, but positive. So I could just do the absolute value. Okay. Hit enter. Yeah, put my parentheses in there. Now I'm good. Okay. Another way I could do this, right, is if I use that norm.s.inv, what is my area to the left here? The area to the right is 0.1. The total area to the left would be what? Yeah, or 1 minus that. So what I could do is say, okay, use that norm.s.inv, and the area I want is 0.9, right? Or 1 minus alpha here. So two different ways of getting the same value, hopefully, if I told you, yeah, right? So we get the exact same value. Okay? There's two different ways of doing the same thing. And then once I've got those alphas selected, I can just copy this down, and it'll give me the critical values for the next three levels, or next two levels, sorry. Yeah. Yep. And you don't have to do both of these every single time, right? You would only have to use one of them. But it is showing you that there's two different ways of finding that critical value. So, if I wanted to, well, here. I can make my rejection, I can make my rejection decision here. So this is what, 1.28, 1.65-ish, 2.33-ish. Here's my rejection regions. Where does my test statistic fall? Well, 2.6 is going to be out here.
right? So my test statistic is in all three rejection regions. Now, what's a way I could check this in Excel? So I can do this, I have a nice visual. I know what the rejection decision should be, reject at every single level. But one thing I said, if we go back, anytime our test statistic is more extreme than our critical value. Now, for a right-tailed test, this is easy. The reason why I say more extreme is because for a left-tailed test, being more extreme is actually going to be a lower value. So one thing we can always do, if I want it just to be more extreme, I'm just concerned with magnitude. Another way of saying that is, if my test statistic, the absolute value, is ever larger than the absolute value of my critical value, this is a situation where, well, it's going to be in my rejection region, so I should reject. So we can actually, and I think it's easier to use the p-value. Like if I ask you to do this on the next Excel assignment, I would probably use the if statement and the p-value approach because I think that's easier to kind of comprehend. But we could have also done, okay, if the absolute value of my test statistic, nope, stop. I just wanted to move it out of the way. There we go. If that is greater than the absolute value of my critical value. Now, in this case, it's kind of redundant to do that because they were already positive values. We're just kind of showing you if we did have a left tail test or a two tail test, it would work, you know, for all of these if we use the absolute value. So if that's true, my test statistic is more extreme than my critical value. It's in my rejection region. I put the word reject. If not, comma, I put the word fail or fail to reject. Now, hopefully I get the exact same decisions as what I made with the p-value approach, right? Now I copy this down, it'll give me all three, and I'll leave this up here for a second. And I'll kind of change some things and we'll see, hopefully these update and give me the same rejection decisions all the time, okay? Any other questions on this before we keep moving? Okay, so this is like, we're just doing kind of what we did by hand, but kind of seeing the Excel version of it. Oh, what did I forget to do? What doesn't change at different levels of confidence? Yeah, my test statistic, right? So I should have been putting cell references there. Now, when I copy this down, now I'm getting the same rejection decisions, right? So you have to remember, yeah, different levels of alpha, your critical value and your alphas update, but your Z statistic, your test statistic, and your p-value, those are always the same, right? We're getting those from the same data, okay? So with 99% confidence here, I could say that I can reject that this difference is less than or equal to 0, or since I had it set up as the Midwest minus the South, I can reject that the Midwest has lower enrollments on average than the South. In fact, I found pretty strong evidence that supports the alternative, which is that the Midwest schools have greater on average enrollments. Okay. Any questions on that before we keep going? Now, one thing we'll also notice, and I'll start to try to make the connection between hypothesis testing and confidence intervals. It's getting at a similar question, just in a slightly different way. So the confidence intervals tells us this is the range of possible values we could see for that difference. The hypothesis test allows us to rule out specific values. So if I'm able to reject that the difference is less than or equal to 0, what values should my confidence interval not include? Well, if my confidence interval is telling me this is what the true difference could be, then it shouldn't include any negative values. Sure enough, if I go back up, even at the 99% level, my lowest bound is still positive. So if I'm looking at my confidence interval, if 0 is ever in my confidence interval, well, then when I go to do my hypothesis test, I know at that level, I should be failing to reject. Because if 0 is in my confidence interval, 0 could be one of those true differences, or between my sample, or could be the true difference between those two groups' means. Okay? But then when I do a hypothesis test for, is it less than or equal to 0? Well, I already know if 0 is in the range, yeah, it could be. So I should fail or reject. If 0 is not in my range, my confidence interval, I know that when I do this hypothesis test, I'm going to be rejected, right? If 0 is not in the range, it's not one of the possible values. Now, there's a little bit of a caveat to that. For now, we'll leave it at that. We'll kind of see the slight difference. Sometimes you could reject, even if it was in your confidence interval, if you have a one-tailed test. But when it comes to a two-tailed test, that will always be true. Right? So for the sake of what we've got right now,
that explanation, just kind of hold on to that. I'll never try to trick you where that won't be true. But there are some, to be complete and theoretically technical, there are some situations where that could occur. So we've got two different approaches of how we do this hypothesis testing, both done in Excel now. Okay. This is what I'm going to now do, something I won't expect you to do, right? But it is kind of interesting, right? So if I find that there is a difference, like I found pretty strong evidence that the Midwest has a greater enrollment, maybe I'm interested in something like, well, can I reject that the difference is less than or equal to 1,000? So really what I'm saying there is, I've got this difference variable. So Midwest minus the South. If I can reject that difference is less than or equal to 1,000, what I'm really saying is, I found evidence that supports that Midwest schools have on average more than 1,000 additional students compared to Southern schools. So it's not that I can just say that they have more or that they have greater than enrollment. I can actually give you a value like, not only is it greater than the Southern school enrollment, it's greater by at least 1,000. Right? So if I change it and I have everything set up correctly, this is where, yeah, we didn't have to subtract 0 earlier, but I wanted to change it to show that you can. Now we've got something where, oh, I can actually reject this at the 90-95% level. So with 90 and 95% confidence, I can say that difference between enrollments in Midwest versus Southern schools is more than 1,000 students, right? The Midwest on average is enrolling more than 1,000 students compared to the South. Now, if I wanted to say at 99% level, now I can't quite do that, right? My p-value was what? 0.025, so not quite low enough, right? But for any example I ask you to do, you can just use that value of 0, okay? Any other questions on anything here before I kind of go back to the slides, kind of introducing the next type of problem we can work on? Okay. So before I do this, let me save this so that I don't forget to save all the work that we just did and have to redo it later. And we'll just keep building on this folder the rest of the week. So on Wednesday, we'll kind of do the same thing. We'll go back to proportions, kind of getting a taste of that again. And then we'll move on to what we're now going to talk about, also seeing an example where I've got two sample means, but I no longer have this nice scenario where somebody told me the population variance. I now only have these sample variances. Right? Well, we did this for one population. What are we going to have to do differently? So everything I have up here, what's the only thing I need to change when I'm calculating my test statistic and confidence interval if I've got a situation where I only have sample variances and I don't know the population variance? Well, everywhere I have a population variance, what am I now going to use? Yeah, the only thing that I have, which is the sample variance for those groups. So the notation changes, just kind of denoting like these standard deviations or these variances all are now just from a sample, right? Sample data, right? I had to use n-1 when I calculated. Well, what's that also going to do is it's going to screw up. I'm no longer going to be able to use z values. We're going to have to use that student t distribution, right? So it's very similar to one population. We just got twice as many moving parts now. So we're going to have to go back and get a little bit more familiar with that student t distribution again, right? But other than that, all the principles, all the steps, everything we've been doing, it's the exact same principles, right? Exact same steps. Okay? So the only other issue that we have is, what was my degrees of freedom before? n-1. So it might be, so okay, at two populations, what would you maybe guess the degrees of freedom is going to be? The difference between the sample sizes -1, maybe I think it's, I add the sample sizes -2 or something like that. Unfortunately, the mathematical proof, we can work through it. We can't simply use the sum of these degrees of freedoms -2. In fact, we could do that if they were the exact same sample size. But in general, the equation that will always give us the degrees of freedom, because here, my group one, let's say they had a sample size of 50, dividing by 49 instead of 50 is going to cause a much larger difference
here, and if the second group is like 1,000, and I divide by 999 instead of 1,000. So how much off from that true population variance I'll be because I'm using a sample variance will depend upon what my sample size is. So unfortunately, we have our confidence interval. I already kind of wrote this up there for us. But unfortunately, how many degrees of freedom? So all of them, we have to use this equation. Now, when I say we have to use this equation, I've just recognized this isn't practice in mathematics, so I've completely dished this when it comes to like the exam. If it comes to like a Excel assignment, I'll show you, I'll give you the function, so you don't have to worry about getting that in. Any type of problem I give you on a homework or the exam, I will give you what this degrees of freedom is. If you had to in practice calculate it, this is the equation that you would use. Okay, so if you wanted to calculate your degrees of freedom, you'd have to do this. Now, really, this is just like a fancy kind of weighted average of, right, each sample means variance, right? So it's the variance of the data over the sample size. It's just some kind of weighted average of those two things. But ultimately, like I said, I'm not going to ever make you compute this by hand. In fact, the next Connect assignment, or the last Connect assignment, if you have to do this, actually, I'll probably only give you some. I'll put this up on Canvas. Any of the problems that talk about the difference in sample means when you have sample variance, I'll give you what those degrees of freedom are, so you don't have to calculate that. So after today's class, I'll put an announcement up. So any of the remaining problems in that Connect assignment, I'll give you what those degrees of freedom are for those problems. Okay. So in practice, though, if we do this and it's not an integer, we would round down. But once we have the degrees of freedom, it's going to look very similar to what we did with one population examples. Okay. So we can go through kind of a confidence interval example. This is the generic steps, right? Everything looks very similar. I'm just using the student t distribution, and instead of population variance, I'm using sample variance. The only other difference, my degrees of freedom equation is really nasty now, but I said I'm going to punt on that and not make it, and I expect you guys to use that. Okay. Whoops, I did not mean to go. There we go. Why does it keep skipping that slide? There we go. All right. So let's say I want to build a confidence interval, and I've got texters and non-texters, right? And I want to know, okay, what's the range of possible values for the difference in response time between these two groups? Okay. So I'm going to get rid of the test statistic equation for right now. We can write this back up if we got enough time to work through a problem with that later today. So I've got two groups, all right? The first step is going to be just identifying, well, I've got each group's sample mean, I've got each group's sample variance, and I've got each group's sample size, right? So I've got 6 of the things that I need. I'm just going to start plugging these things in. So I've defined this as the difference between non-texters and texters. So my group 1 is these non-texters. So 1.3 minus 2.36, that's the sample difference I found. I don't know the t-value yet, but I know what the variance of each group is. So 0.16 over 49. And then the second group's sample variance over that group's, where's their sample size? 64 drivers, right? So these confidence are like, you'll have these formulas in front of you at this, on the exam or on some of these problems, you're going to be given this information, just a matter of getting these values plugged in. Okay. Once again, it might be helpful to calculate this as a separate value, so you just have one value to plug in there. The only other thing we need to do is what t-value gives us a total of alpha on either side, a total of alpha outside of our interval, but we've got 2 sides, so that means that there's half of alpha on each side. This is identical approach to what we just did with the example we had in Excel. The only difference is can't use that standard normal. We have to use one of these student t distributions. Which one do we use? Well, this is where we're going to cheat. I'm going to plug all this in for us, not make you have to calculate this by hand. We've got this degrees of freedom of 80.39. Well, if we look at that student t table, right, all our degrees of freedom are integers. So we always kind of err on the side of caution and make it a smaller degrees of freedom, right? So 80.39, we're going to make 80. If it was 80.99, we'd still make it 80, right? We kind of wouldn't, I call it this, and it's not really a technical term, but it's the name of the function in Excel. It's like you're flooring that variable, right? You're just, even if it's 0.99, you push it down to the next lowest integer. Okay? So we got this degrees of freedom of 80. So how can we find this value by hand?
I'm gonna scroll down here. Oh, and I think I forgot. So this was the 90% confidence interval. So what should my alpha be? Yeah, 90% alpha is 0.1, which means I've got 0.05 in each tail. So that's the area I want in my tail. So that's this column right here. And then I'm going to scroll down till I get to a degrees of freedom of 80, 1.664. That's the last thing I needed. Now it's just a matter of getting this entered into my calculator. I mean, we're not really reinventing the wheel here, right? We're taking what we did with the one population only having a sample variance examples and what we did with two group sample means when we knew the population variances, and it's kind of like just mixing those two, right? Especially since I'm not making you do those degrees of freedom calculations. Any questions over anything here before we keep moving? So go back here. I can get this to pop up for me. There we go. So here's my meme. Anybody know what movie this is from? Nobody? You should all watch Office Space. It is one of the funniest old movies. Like it's great. It's a classic. If you've ever seen it, I have a red swing line stapler in my office, which should cause concern if you watch the movie. You'll know why. So, anyways, we've got this lower upper bound. Why am I saying we should stop texting and drive? If I've only got negative values here, right? Negative 1.3 to negative 0.79 with 90% confidence, what could I say? So if I've defined this as my non-texting group minus my texting group, and I'm telling you the range of possible values, is negative 1.3 to negative 0.79. What are the only values in that range? Negative, which would imply that this difference is less than 0. In order for this to be less than 0, that would mean the response times for people who are texting while driving is greater than the response time for people who aren't texting. When you're driving, higher response times are not good things, right? So this would kind of tell us with 90% confidence, texting while driving is causing people to be slower, right? Their reaction times are higher. Okay. Any questions on that? Yeah, sometimes like when you're thinking about making these statements too, it helps to kind of write it out, right? In fact, if I did have this written out, one thing I'll sometimes do, even for myself, if I know that there's only negative values, it's kind of easy to think about, oh, okay, the difference is less than 0 then. Well, how do I actually, compare these groups? I'm going to move this group to the other side. And now I kind of can see from here, oh, response times from texters is on average higher, right? And that's usually how we would speak. I mean, sometimes you'll use, talk about the difference, but a lot of times we want to compare this group to the other. Questions on that? Keep moving here. So, got this example, right? And just to kind of get a little bit of practice, and then we'll kind of end on this. So, let's say I had two different brands of cigarettes and I had their different nicotine levels. So I've got their sample means, sample variances, sample sizes. I want to build a 95% confidence interval, right? And I've got degrees of freedom of 42. So I'm going to give you guys a couple minutes to work on this. We'll then kind of come together, talk about it. So very similar steps to the last problem. I've got two different groups. I'm interested in the difference between group A, cigarette brand A, cigarette brand B, right? You got the means, sample variances, sample sizes. I need a 95% confidence interval, so I'll even help you out here. 95% confidence will be an alpha of 0.05. I've given you this degrees of freedom, which is 42. But if you plug these variances and sample sizes into that equation, you get a degrees of freedom of 42. So with that, using the student T distribution, I just want to make sure that we can kind of hopefully plug these values in, look up that T value. It gives me alpha and 2 on either side. Give you guys a couple minutes and we'll kind of come together. Let's see kind of where we're at in terms of working through these.
so I want you to think carefully before you answer here. So if we're defining this as cigarette brand A minus cigarette brand B, who of these answers shouldn't make any sense? So even if you haven't completely worked through the problem, look at these answers and answer with, you know, basically you have a 50-50 guess. I'll give you credit if you guess either of the ones that could just be potentially the confidence interval. So think about what we're doing with confidence intervals. You define this as cigarette brand A minus B. You're building your confidence interval around that sample difference. So that sample difference should be smack dab in the middle of your confidence interval. So which of these, you know, you're taking a guess, make sure you're guessing one that would be true about. If you haven't worked through it completely, that sample difference, right? Whatever answer you choose should be smack dab in the middle of that interval. So that in mind, you haven't gotten an answer in. Take your best guess here. I think I counted 23, but I could be wrong. All right, everybody got a response in, all 23 of us. There we go. Ready to look at this, but which of these should not be a possibility to be the correct answer? B, why? What's the sample difference we found? A is less than the sample of B, so we're gonna have a negative difference. So not only do we have a negative difference, I think it's what, negative 0.27. What other value or other confidence I can't meet there? Yeah, why? Negative 0.27 isn't even in that confidence. Right? So right away, we should either think is C or D. Now I think the difference is, I think C is one of those if we accidentally use like the standard normal distribution as opposed to the student T. But hopefully, right, we can at least rule these out right away. Okay. Now, if you had made a mistake and maybe flipped cigarette, you know, what group was one and what group was two, potentially gives you the other one. But yeah, we should be able to rule A and B out right away. From there, it's just a matter of identifying what we were given. If I've got degrees of freedom of 42, my alpha was what? 0.0, actually, was it a 95% confidence interval? Yeah, so alpha was 0.05. Well, that means I have half of alpha on each side, so 0.025. So I go up. I wanted 0.025 in that tail. Degrees of freedom, 42, 2.018. Now it's just a matter of being able to get this entered in my calculator. If you're having difficulties with that, kind of try to rework some of these examples on your own. The Connect assignment has a few you can work on. Other than that, we'll do some hypothesis testing with these types of examples. Do some more Excel work on Wednesday. You might see the next Excel homework pop up. You probably get started on it, but we haven't worked through everything completely yet. Okay. All right. I'll see you guys on Wednesday.